So that leaves us where we're at right now, and that is that they thought of atoms as a whole. So the next thing, and think about time frame. Thomson, same time as the American Revolution, late 1700s. The next person who comes along is J.J. Thomson, John Joseph Thomson, I think, or Joseph John, I forget which one, but he went by J.J. Okay. He was an English physicist, and he did most of his work in 1897. So we have another 100 years before anything changes about the atom. And notice I put here a physicist. Okay? Physicist, not a chemist. It's a physicist. Actually, it caused him some problems along the way. Okay. And so what he wanted to explain was they had this device called a cathode ray tube. Okay. But they didn't know why it worked. Okay. So I gave you the Thomson's experiments models. This is what the actual cathode ray tube looks like. Oops, I'm in the wrong place. So, play.
Electrons are high-energy particles that have mass.
Okay, so this wheel is spinning. Okay? Something has to make it spin.
You can't...
Oops, stop. Pause. Okay, so let's go with what it is. Okay, that wheel is inside this glass tube. Okay? The glass tube is connected to a battery. One at one end. This side is called the anode. And this side is called the cathode. Okay? And when they turn it on,
you can't see the electrons as they move through the tube, but you can observe the effect they have on the wheel.
They turn it on, the wheel spins. Oops, go back. So when they turn it on, the wheel spins.
The tube, but you can observe the effect they have on the wheel.
Okay, so what that tells them is something has to be going from here. Oops, it's the wrong one. Has to be going from here to there, because that's the only thing that would push this wheel around in circles. And that whatever it was had mass. So they knew that a ray coming off the cathode had mass enough to move a wheel. So they could check to see whether it had mass. Okay. Then, let's see here just a second. There it is. Okay. And to see what they were saying,
a cathode ray.
Okay. So here's a cathode ray tube. The way we look at it. Okay. So there's our tube. There's our two plugs to the battery. And they put a white screen in here. And that white screen is covered with phosphorus. And phosphorus glows when it's hit by charged particles. So if you ever looked at fluorescent lights, you'll see that they're all covered on the inside with a white powder. That white powder is phosphorus because what happens is charged particles hit that and that white powder glows. Okay? So they can actually... So now...
Tube illustrates the charged nature of electrons.
Okay? So they can tell it's coming off this end. This is the cathode end. So the ray that comes off the cathode is called a cathode ray, and the tube that holds it is called a cathode ray tube. Okay? So they turned it on. They could see, they knew it had mass. The fact that it shows up here means it has charge, and also the fact that you can move it with a magnet means it has charge. The fact that the magnet moves the beam around. Now notice, When the south is away from us, it goes down, but when the south is towards us, it goes up. Okay. That's because magnetism and electricity are always at right angles. So this is the device
Nature of electrons.
that Thomson was trying to explain. That was his goal. His goal was to explain how that thing worked. Okay? Nobody knew. So, but he was a physicist, so he was comfortable working with electricity and magnetism. Okay? Come on, get off my screen. So he was comfortable working with electricity and magnetism. He knew how to work with them. I can't get this off my screen, and it won't shrink. There it goes. Let me drag it off. Why did you get maximized? Okay. So he was looking at a piece of equipment called a cathode ray tube. Okay? A cathode ray tube. Okay? So it's a tube where there was a cathode ray. Okay? And nobody knew why they worked. That was his goal. He was not trying to find out anything about atoms. He was a physicist. He wasn't worried about atoms. Okay? Okay, so that cathode ray tube is a vacuum tube. A vacuum. A vacuum is a place where there's no air. Okay? So what they do is they take that glass tube, and after they put all the stuff inside, they seal it and pump out all the air. And just because I misspelled it for the first 25 years of my life, that is the correct way to spell vacuum. It has one C and two U's. I always spelled it with two C's and one U. So vacuum, it's the only word I know of that has a double U in it. Okay. Okay. Now they did actually put in just a little bit of other gas. A little bit of gas. They found they needed a little bit of gas for this to work. Just a tiny little bit. Okay. Inside you got metal discs. This one is called the cathode. This one is called the anode. Okay. So if I turn on the power, a beam moves from the left-hand side to the right-hand side. From the negative to the positive, from the cathode to the anode. So it's a ray that comes off the cathode, a cathode ray. Now we saw on the video that they could move this around with a magnet. You can also move it around with charges. And if you put a positive charge on top and a negative charge on the bottom, it bends towards the positive charge. Or you could equally say it bends away from the negative charge. And that told him that whatever was moving had a negative charge. It had to have a negative charge, so it bent that way. Okay, you've all heard the expression opposites attract, and what they mean there is electrical opposites attract. Negative and positive attract each other. Or you could also say it was pushed away by the negative charge, because like charges repel. Okay? Just like on a magnet, the north and the south attract, and the north and the north repel. Likes repel, opposites attract. It's a big idea. So the fact that it turned told him it was negative. The fact that it spun the wheel told him it had mass. Okay? And he used different metals to make his anodes and cathodes out of. When he put that gas in, he put different kinds of gas. But no matter what he did, the beam was always the same. It always turned the same amount. So let's think of what we got now. We got a negative thing with mass that shows up no matter what substance I put into it. Okay? And when I say the same, he actually found the ratio of the charge to the mass. And it was the same no matter what he put in there. So if you take the charge and divide it by the mass, you can get a number. Now, that's all he could measure, because how fast something turns is affected by two things: how fast it's moving and how heavy it is. If something is light, it is easy to turn. If it's going fast, it's hard to turn. So what that leads to is light and light with a big charge. Light with a small charge looks the same as heavy with a big charge. You can't tell the difference between those two. You can tell that what the ratio has to be the same, but if the piece is light, it's a small charge. If the piece is heavy, it's a big charge. Okay? And I tried to show you that with the simulations that you guys looked at over the past couple days. So on this one, oops, you see it? There we go. On this one, okay. On this one, all I asked you to do was to turn it on. Okay? And then we could adjust the charge on plates. So if it had a negative charge, or a very high positive negative, it would turn a lot. The higher the charge, the more it turns. And the more negative the charge, it turns. And it didn't matter what you made the electron out of. Same beam. Okay? So then I had you look at this one. Drag it over there. Okay? So, same type of thing. You send a cathode ray particle, and it moved towards the positive. Okay? Because it had a charge. If I turn the charge on very high, it turns more. Okay? Now, that was a cathode ray particle. Over here, we say it's negative. What happens if I send a negative atom? If I send a negative atom, it should turn up. But nothing happens. Okay? And that's because this is much heavier. I need to increase the charge by 1,000 times before I can get it to turn. It takes a lot more charge to move something, to turn something that's heavy, like an atom, than it does to turn something that's light, like a cathode ray particle. So from this, he could tell that whatever piece it was smaller than an atom, It weighed less than an atom because the cathode ray, if you shoot there, doesn't make it past the first plate 1,000 times. Makes it turn hard. If I send a negative atom, it turns the right direction. If I send a positive atom, it turns the other direction. But it turns much less than a cathode ray. I mean, let's turn it way down. No matter with that 1,000-fold, no matter how far I turn it down on this slider, it'll only let me the lowest notch. Even the lowest notch goes right to it. That's because it's 1,000 times heavier. Okay? So, what we know about the atom is he could find the ratio of charge to mass, and it was the same with every material. Okay. So, there's one last one I couldn't show you because it was a flash one, and flash doesn't work on your computers. Okay. But this is a little bit more like what Thomson's equipment looked like. If I can get it to show up on the screen. It cuts off the left-hand side, right-hand side. What's going on? Zoom? Ah, there it is. Okay, so on this one, this is actually what he actually set up. So we saw cathode rays. This is his cathode ray, and you send the cathode ray without a charge. It goes straight through. You add, you've got E for electrical charge, and now there's a positive here and a negative there. So when the particle goes through, it turns a little bit. And the higher I turn up the charge, okay, the more it turns. But it always turns up. They set it up so it always turns up when I turn up E. Now B is the unit for measuring how strong a magnet is. So they put a magnet next to it, and we saw a magnet does it. And so a magnet is set on the outside of it, and you push it, and it turns the other way. So he's got it set up so that electricity makes it turn up, and magnets make it turn down. Okay, so he's got two opposite forces here. And what he did was he tried to balance them. So he turned on the electricity to try to counteract. That. And it did go far, so I got to turn the electricity up a little bit more. It's pretty close. It went down a little bit. Still a little bit down. Oops, too much. So you get that. And what you can tell from that is the ratio of E to M. Oops, what did it do? Okay. So from that, he can figure out the ratio of E to M. Electricity to magnetism. Charge to magnetism. And what he found was that no matter what material he made it out of, he got something near 0.172, no matter how much charge he put here. He got 1.72. Doesn't matter if he made it the biggest one. Oops, it didn't show up. It was 1.72. I don't know why I didn't do that. So it doesn't matter the biggest one or the smallest one, and it didn't matter what he put in there, he always got that same ratio, about 1.72. Now that 1.72 is in some bizarre units, so we're not going to worry about those, but the key is he got the same number every time. So that told him, this is the conclusion, the only thing that explains all of those things, the only thing that explains all the facts we have, that no matter what I put it in, I get the same kind of piece with the same bend, and since everything's made of atoms, that means this has to be a part of every atom. And the chemist went, "You're wrong." Why would I listen to a physicist? You don't know anything about chemistry. What are you doing talking about atoms? And so the book talks about the idea that Thomson did this in 1897, but the idea of electrons wasn't really adopted until about 1910. It took about 15 years for it to really percolate through chemists, because they said it's got to be, you're a physicist, what are you doing studying chemistry? So I'm not studying chemistry. Chemistry popped out on me. I was trying to figure out how this cathode ray worked, and the only thing that explains it is little particles with a negative charge. So he found those little particles with a negative charge, and that little particle with a negative charge we call the electron. Now, he never found a positive piece. People later on did eventually, but we're actually not going to talk about how they did it, but he didn't find a positive piece. But he knew there were negative pieces. So how do you have a neutral atom if you've got negative pieces? Well, that negative piece has got to be with some positive stuff. So he said, the atom is like plum pudding. Which makes perfect sense if you know what plum pudding is. But most of you probably don't realize that plum pudding is raisin bread. Okay? To English people, if you mix stuff that doesn't mix real well, it's called a pudding. Okay, so it's like raisin bread, except it's got a spicy bread, so it's like a fruitcake with raisins in it, and that's plum pudding. So if you think about it, raisin bread, because it had a positive stuff that was like the bread dough, with negative pieces stuck into it, like the raisins in the raisin bread. So he said, okay, we've got this bunch of positive stuff, and there's negative pieces that can fly out of it. And that explained everything he saw in the cathode ray tube. So he had to change the picture of the atom in order to explain cathode ray tube. The model of the atom changed. Before Thomson, everybody thought the atoms were just spheres that weighed different amounts. And the atom explained weights, but it didn't explain chemistry. You could remember some stuff about chemistry, but it didn't explain chemistry. There was no reason why you couldn't talk about a reason why this reacted with that in terms of atoms. All you had was laws that this tended to react like that. You didn't know why. Okay? So that's what Thomson said it was like. Okay. So the next person on the list wanted to figure out what Thomson couldn't figure out. So Thomson could figure out the ratio of charge to mass, but he couldn't get charge and he couldn't get mass. But once you got charge or you got mass, then you got the other one automatically because you had the ratio. So if you can find a way to find the mass of an electron, then you can find the charge of the electron. Or if you find the way to find the charge of the electron, then you can find its mass. So the person who did that was Millikan. Now this is not the Millikan that the street's named after. The Millikan we know was named after a rancher here in the Cucamonga area from the 1800s. Robert Millikan. But it's spelled different too because it's spelled with an A. Okay, so he made this kind of device. Okay. And what's in this device? Well, first of all, you got a little container of oil. And it's in a spray bottle. The spray bottle is called, curiously enough, an atomizer. Tear it apart into pieces. It really doesn't tear it apart into atoms, but it makes little tiny drops of oil, like a mist of oil. Tiny drops that you can't see. And he's going to spray it inside this device, and he's going to have a microscope so he can see those tiny drops of oil. So he's got a way of making tiny drops, he's got a way of seeing them. Inside the container, there's some metal plates. And those metal plates are just there so that they can put a charge, a positive and a negative charge. That's what they're there for. But you'll notice the top plate, since I cut this in half, there's a hole right in the middle of it. There's no hole in the bottom, but there's a hole in the top, and that's a place for oil drops to fall. So that when you squeeze the atomizer, a few drops are going to fall straight down. So he's got a way of making tiny drops of oil that he can see with a microscope that are falling straight down. Okay. Along the way, those oil drops get hit with X-rays. That's why it's all sealed in this container. A, to keep it air-free. B, so you don't get hit with X-rays. And what X-rays do, the X-rays give the drops a charge by knocking off electrons. It knocks some of those electrons off. Now, he can't control how many electrons it knocks off. It may knock off 1, it may knock off 35. He has absolutely no control over how many it knocks off. But he knows it'll knock off electrons because he can check the charge on the oil drops. What charge would the oil drops have? Well, they were neutral before, and then you knocked off an electron. So what's left is a positive oil drop. Okay. So when the X-ray hits the oil drop, oops, it knocks off the electron, and you get a positive drop of oil floating down. So all of this has been set up so that he could have a microscopic drop of oil fall straight down and be able to see it fall. Then he put electric charges on the plate. Put a positive charge on the bottom and a negative charge up top. So that means this drop right here is being pushed from the sorry, got those backwards. Oh no, he's got a positive drop of oil falling. So that drop of oil is going to be pushed by the positive, and it's going to be attracted to the negative. So you got two forces. Gravity is pulling it down, and charge is pushing it up. And he could adjust the charge. He could turn a dial on that charge, give it more charge or less charge. And by adjusting the dial, he could make some drops hover. He could catch the drops. They would hover because the force of gravity has to equal the force of the charge. That's how this is all set up. So let's see if I can show you what we're talking about there. I haven't got good at this yet, but okay. So this is simulation. So we got drops. Oops. Let's restart this. Is there a way to? Okay. So got oil drops. I have no charge. So if I just push start, the oil drops are just going to fall, and gravity is just going to pull them down. Okay. They fall. But when I turn up the charge, if you focus on one specific one, I can get them to move upwards. But what I really want to do is I want to catch one and make it not move at all. So I'm going to focus on that one. Can I stop it? I can't give it enough charge to stop. Okay? And you can adjust it so that one drop would hover. Okay? Oops, got to turn up a little bit. Okay? Does that make sense? That he's going to make the drops hover. That's the whole goal of this whole thing. Okay. So first of all, he could calculate the mass of the drop. Say, what? Okay, well, he's got a microscope and he can measure the radius of the drop. From the radius of the drop, volume is 4/3 pi r cubed. So if you get the radius of the drop, you plug that in here, you've got the volume. And mass is density times volume. So you figure out the radius, that'll tell you how big it is, and then you plug that volume in here, and you can figure out how heavy that drop is without weighing it. Just by so that was a bizarre use of the density equation. We're expecting density to show up right here, but he used the density of the oil to figure out how heavy that tiny drop was. It was really tiny. Okay. Okay. And it says calculate the charge on a droplet. No, he calculated the charge on an electron. Oh no, actually, it's right. He did. No, I'm ahead of myself. He's going to the electron, but he got the charge on the droplet. And the reason why that's important is because every droplet is different. Okay, let's restart this. Okay. They start off falling, but when I turn on the power, different ones are affected different amounts. Notice how some go up really fast. Now those don't have very much. Those have a lot of charge. The ones with lots of charge get pushed away. The ones with little charge don't get pushed very hard, so they keep falling, but they don't fall as fast. So I turn off the field, everybody falls. As I turn it up, they fall at different rates because they have different charges. Every drop is different. So you could figure out the charge on each drop, and it wasn't the same. So he calculated the mass of the drop from density and volume. He calculated the charge because think of what affects the force of that thing going up is the force of the charge, and that depends on the charge of the particle. So you can calculate the charge from the mass pushing down and the charge on the plates going up. And this one just went bad. Give me a second. Let's see if I can find the right one. I'm trying to open up another file. So I had the numbers. They were there. And I just crashed my computer. Yeah. It just crashed on me. I apologize. So, get that back up here for a second. Sorry, my computer crashed. I wanted to show the numbers. It's doing something I can't see. What the heck is McAfee scanning? I don't have McAfee. Might just have to give up, give you those numbers a little bit later. Okay. One last shot and then I'm going to give up. Tired, wait for this to not crash on me. There it is. That's the one I wanted right there. Okay. So he was only finding the charge on the drops. Okay. That's all he was finding. And he got a bunch of numbers. Now his numbers didn't look like this, but when you get a bunch of numbers like this, what do you notice about them? You know anything about those numbers? Well, they all have a factor of 3. Everything in there is divisible by 3. Their greatest common factor is 3. Okay? Ooh. Never thought I'd hear math words like greatest common factor anyplace else, but greatest common factor. So he looked for the greatest common factor in his numbers because he knew he had to have pieces. Okay? So that piece had to have a charge. So the common factor would be how big the charge was on one piece, because the oil drop either had to have one of those or two of those, had to lose 1 electron or 2 electrons or 3 electrons or 4 electrons. He couldn't control how many, but he could look for the greatest common factor. And when he did that, he found that the greatest common factor was 1.60 times 10 to the negative 19th, and C is the unit of charge And that unit of charge is coulombs. Oop, I forgot the U. Coulombs are the unit of charge. So if you remember, that Thomson had found this ratio. He found it at the ratio. So once he finds that ratio, we now know charge and we know the ratio, so we can find the mass. So by finding the charge on one drop, he could then calculate the mass of that piece by how fast it bent. How much charge would it take to bend that much? So this was the ratio he'd found. So he took and multiplied that and found out that that was the mass of an electron. And people didn't believe him, because this number is unbelievably small. If you took a paperclip and cut it into 1 billion pieces, and then took one of those billion pieces and cut it into 1 billion pieces, and then took one of those pieces and cut it into 1 billion pieces, it would still be 10 times heavier than an electron. Okay, electrons are really tiny. Notice atoms are tiny, but if you remember the simulation, atoms are tiny, but they were much harder to turn than the electron. So that means the atoms had incredibly tiny masses. Okay, so that's where I want to stop for today. Okay, and with what I want to do instead is